Good morning. How was the quiz? Good? Difficult? Nope. Good to hear that. Okay, any questions on quiz or filter?
Will the quizzes mostly just be 2 questions, or will they go more into detail?
Usually 2 questions. Okay, filters. What are filters? One of you please explain to me filters.
Only takes one frequency. Either lower
Not just one frequency,
the range of frequency.
a range of frequencies. For example, if we had a low pass filter, it would pass low frequencies. Okay, just the range. We call that range a band. So for example, for this filter, what kind of filter is it? This one, the first one, what's that? A low pass filter. Why? Because you see from 0 to omega c, which is our cutoff frequency, we call it pass band. So the frequencies between these two values are pass, and after that they are not allowed to pass. So we call this band stop band. So this is a kind of low pass filter, again an ideal low pass filter. Why? Because this is very sharp over here, and in practice we don't get such a filter, so we have something like this. So how about this filter? This is a high pass filter. So from 0 to omega c, which is our cutoff frequency, is our stop band, and after that frequencies are allowed to pass, so we call it pass band. And this one, the third one, is an ideal band pass filter. So we have two cutoff frequencies for a band pass filter. Omega C1 is our lower frequency and cutoff frequency, and omega C2 is our higher cutoff frequency. So between omega C1 and omega C2, whatever frequencies we have, they are passed, but below omega C1 and beyond omega C2, they are not allowed to pass. So we call this kind of filter band pass filter. And for the fourth one, which is band reject filter, again we have two cutoff frequencies. The first one is the lower cutoff frequency omega C1. This is omega C2, sorry, just corrected in my notes. Omega C2, so below omega C1, the frequencies are passed, and between omega C1 and omega C2, frequencies are not allowed to pass. So we call this band stop band. Again, after omega C2, we have a pass band. So this is an ideal band reject filter. Any question on that? And Aiden asked me, how about these plots you have over here? As you see theta, what do we call theta? I explained it on Wednesday. The phase angle, yes, that's correct. So there are phase angles. For this is one, the phase angle for ideal band pass filter and the phase angle for band reject filter and for low pass filter and high pass filter. So how do you calculate the phase angle for a filter in the frequency domain?
Isn't that like, do you have like the transfer function and it's the
Okay, before imaginary part over real part, we have something. Tan in, yes. Okay, so first, if you want to calculate the phase angle, first find the transfer function. From the transfer function, get the tan inverse, the imaginary part over the real part. Any questions? So what is the cutoff frequency? The magnitude of the transfer function at the cutoff frequency. So this is the transfer function at the cutoff frequency, and these two lines mean magnitude. So the magnitude of the transfer function at omega c, which is the cutoff frequency, equals 1 over square root of 2 multiplied by h max. What is h max? The maximum value for the transfer function. So if you find, first of all, you have to find the transfer function. So once you have the transfer function, find the maximum value for the transfer function, which is h max. And if you multiply it by 1 over square root of 2, so you will get the magnitude of the transfer function at the cutoff frequency. Any question? What you learned before, what kind of filters? They were passive filters or active filters? Before this class? Passive. Why passive? Because you had passive components. Like what? Like a capacitor, like an inductor, like a resistor. But over here in this circuit, you see an op amp. This is kind of filter. Is it a filter or not, this circuit? Could it be a filter or not? Yes. How?
Susan with an op-amp, you have to go between those two negative 10 to positive 10 to actually have a reactive.
Negative what? Negative.
Shifting two numbers that you should use the negative 10 to positive 10. Those are actually two.
So, okay, 10 minus 10 and positive 10. Are you talking about the power supplies connected to this filter over here?
Yeah.
Okay, so this power supply is connected to this op amp, for example, positive 10 volts and minus 10 volts, they are constant. So they are not changing. So positive 10, negative 10. Whenever we are talking about filters, for sure we have alternative source connected to our circuit. So VI is alternative. If it wasn't an alternative power supply, would you have a filter over here? Why? Okay, so why? No frequencies, why?
Capacitor which is charged.
Capacitor just charge and after a long time,
Just be the same value.
okay, yeah, just open circuit. It will act as an open circuit. Okay, so why here? But if the frequency changes, what would happen to the impedance of the resistor? When the frequency changes because of the power supply, what will happen to the impedance of the resistor? The same. How about this resistor, the second one, R2, because this is a resistor, again the same. How about the capacitor, the impedance of the capacitor? Will change. Why? Because the impedance of the capacitor is 1 over j omega c, or in the S domain is 1 over SC. So what will happen to the circuit in low frequencies? In low frequencies. Because we have low frequencies, what would happen to the impedance of the capacitor? They are very high. So if the impedance of the capacitor is very high, so capacitor acts like an open circuit or a short circuit. Open circuit. Now impedance is very high. So because of the impedance of the capacitor is very high, the capacitor acts as an open circuit. So for low frequencies, capacitor acts as an open circuit. So this is open circuit. So it means no capacitor over here. So what kind of circuit do you have over here? After quiz number 1, you said the questions were simple and fair. So what kind of filter do you see on the screen? What's that?
Inverting amplifier.
Inverting. Is this one an inverting amplifier at low frequencies? Yes or no? So for low frequencies, impedance of the capacitor is high, so the capacitor acts as an open circuit, so you have just this circuit. So what is this circuit? This is an inverting amplifier or op-amp, operational amplifier. So what is the gain of this amplifier? Minus R2 over R1. What is minus R2 over R1? What is the relation between the output voltage and the input voltage over here for this circuit? What is that? The relation between the output voltage and input voltage, which is our transfer function. Do it, please. Find the relation between V out and Vi when the frequencies are low. So for low frequencies, find the relation between the output voltage and the input voltage.
V output equals to Vi into negative R2 over R2.
So it means V out over Vi is
Equals to V input into negative R2 over R2.
no, again V naught over Vi equals
Negative R2 over
negative R2 over R1. Yes? Is he right? What is the voltage VP? VP 0. How about Vn? Of course 0, because we assume that this is an ideal op-amp. So Vn minus Vi over R1 plus Vn minus V out over R2 equals 0. So what is the relation between V out and V in? Minus R2 over R1, which is the gain for this circuit at low frequencies. How about high frequencies? At high frequencies, when the frequencies are high, so the impedance of the capacitor is 0 or it's low, or at very high frequencies we say 0. So when it is 0, the capacitor acts as a short circuit. So this is a short circuit. If this is the short circuit, look at here please, V out is 0. Why? Because VP is 0, Vn is 0, so this is a short circuit. It is like V out is grounded, virtually grounded. So V out, or the output voltage now, is 0. So at high frequencies, V out is 0. So the frequencies are not passed. So this is a low pass filter. Any question on this circuit? Clear? Okay, the above circuit is something like this. We have ZF over here. So what we had over there, a capacitor in parallel with R2. So I put them inside the box and I called ZF, the feedback impedance, and over here ZI. This is input voltage and this is our output voltage. So find the transfer function for this circuit. The transfer function is V out, the output or the response, over Vi source or the input. So what is the relation between V out over Vi? How do you calculate that? I just explained. For low frequencies, for high frequencies, because of the capacitor, no frequencies are passed. So at low frequencies, we have minus, this will be like an inverting amplifier. So we have negative ZF over ZI. So what is ZF? The feedback impedance. So here we have a capacitor in parallel with a resistor. So how do you calculate the impedance, the equivalent impedance of these two components? R2 in parallel with the capacitor. So it will be R2 multiplied by 1 over SC over R2 plus 1 over SC. And you have minus 1 over R1 over here. So you will get this. If you rearrange the equation, you will get this final equation. So R2 over R1, we call it K, which is the gain. And 1 over CR2, we call it omega C. What is omega C? The cutoff frequency. Why the cutoff frequency of this circuit is 1 over CR2? Why did I write 1, instead of writing 1 over CR2, I wrote omega C. I call this term cutoff frequency. Why? How do you calculate the cutoff frequency? One more time. The magnitude of the transfer function at the cutoff frequency equals 1 over square root of 2 multiplied by H max. What is H max? The maximum value for the transfer function. So please try and find the cutoff frequency for this circuit. Now, do it yourself. Otherwise, you will not learn. Any answers? If you have my notes, go to page number 5. Okay, so we said omega c, the cutoff frequency is 1 over R2C, and we are going to prove it. So what is the equation for the cutoff frequency? This is the equation. The magnitude of the transfer function at omega c, which is our cutoff frequency, equals 1 over square root of 2 multiplied by h max. What is h max? The maximum value of the transfer function. So what is our transfer function in the frequency domain? This is our transfer function. V out over Vi, the ratio between the output to the input. So this is the transfer function. So what is the maximum value for the transfer function at low frequencies? Why low frequencies? Because this is a low pass filter. So what is the maximum value for this one? The maximum value for the transfer function. What is the H max?
It's 1 times the constant k, where in this case it would be your transfer function.
The maximum value, what is the maximum value of the transfer function? Is it the transfer function itself?
Well, it's
Negative or zero.
What's that?
When the frequency is zero, it will be the maximum. Negative or 2 over R1.
For low frequencies. Is what's Walter?
Negative or 2 over R1.
Negative R2 over R1. Why?
Because negative 0 times the same on top of the right, the same at the bottom, just 1.
Yes. You have two options. One, you can say for high frequencies, when omega is high, so this at the bottom we have high infinity, so 1 over infinity is 0. So that cannot be our values. But because the second option, because this is a low pass filter, so we just consider the low frequencies. So at low frequencies, for example at 0, because they are very low, so something very small plus 1 over R2C will be 1 over R2C. So 1 over R2C over 1 over R2C is 1 multiplied by minus R2 over R1. So that is the maximum value for the transfer function. So now you have the value for the for H max. You just put it over here. So how about the magnitude of the transfer function at omega c? What is the magnitude of this function? How do you calculate? The magnitude of this one is R2 over R1. The magnitude of this one is 1 over R2C because this is real. How about the magnitude of this one? This is a complex number. What is the magnitude? What's that, Josh? Yeah, or the square root of the real part squared plus, this is the real part squared over here, plus the imaginary part squared, which is omega c squared. Okay, is that clear? Do you follow me? Yes? Okay. So this one, on the left hand side of the equation, you see the magnitude of the transfer function at the cutoff frequency, and on the right of the equation, you see 1 over square root of 2 multiplied by H max. So get this squared from both sides of the equation, you will get this. So these two guys will cancel out each other. you will get this part. So from this part, 1 over 2 multiplied by 1 over r2c squared is equal to omega c squared plus 1 over r2c whole squared. So omega c squared is 1 over r2c squared. So omega c is 1 over r2c. Why not minus 1 over r2c? Okay, from here, omega c squared is equal to 1 over r2c squared. So omega c is plus minus 1 over r2c. But we just accept 1 over r2c. Why? We have. We are going to just consider for our filters from 0 to positive infinity. We don't care about that side of the band. That's why we just accept 1 over r2c. Any question?
Did you have to did you have to square it there to get like rid of both sides? So when you had the magnitude of
This one?
yeah, did you have to square it there?
If you know any other solution, you go ahead and do it. Because it is the easiest way to find omega c. You don't have to, but this is the easiest way for me at least. Okay, now you know how to calculate the cutoff frequency for filters. Okay, I'm going to explain it one more time. If you want to calculate the cutoff frequency for any filters, first you need to find the transfer function. Once you find the transfer function, find the maximum value for the transfer function and multiply it by 1 over square root of 2. This is one side of the equation, and the left side of the equation is the magnitude of the transfer function at omega c. You need to find that. So from there, you will find the cutoff frequency. So that's why for this circuit, R2 over R1 we call it K, which is the gain, and 1 over CR2 we call it omega C, which is the cutoff frequency. So the transfer function is minus K multiplied by omega C over S plus omega C. Any questions? Body plots. Did you study this kind of plots before? Okay. A body diagram or plot is a graphical technique that gives a feel for the frequency response. So for example, when we use body plots, from the plot we can understand about the gain of the filter. From the plot we can understand what kind of filters we have, and from the plots we can understand the cutoff frequency. So it is very easy. We have a plot. If you show me the plot, I can understand what kind of circuit you have. It is a low pass filter, high pass filter, or whatever, and I can understand about the cutoff frequency or cutoff frequencies, and I can understand about the gain of the circuit. So that's why we use body plots. So what's the difference between body plots and the frequency response plots we used before? What is the frequency response plot? We used it before. It was the magnitude of the transfer function versus the frequencies, right? But now, instead of using a linear axis for the frequency values, we use logarithmic axis. What is the difference if we use logarithmic axis instead of linear one? Why are we interested in using logarithmic axis?
Make it look linear.
We make it what?
Here linear on the plot when it's actually not. It's like exponential.
No. Thanks for the answer, but no. Why do we use logarithmic axis?
So that we can get wide.
Yes, because sometimes we have very big range of frequencies and we want to plot everything in a very small plot. So if it is a linear axis, we cannot because it is a wide range of frequencies. But if we use logarithmic axis, so we can plot wider range of frequencies. That's why we use logarithmic axis, okay? So wider range of frequencies. That is the answer. And instead of plotting the absolute magnitude of the transfer function versus frequency, now we plot the magnitude of the transfer function in decibels versus the log of the frequency. So what is the decibels? dB. I explained it before. The magnitude AdB is the magnitude of the transfer function in dB, okay, is 20 times log the magnitude of the transfer function. What is the base? The base is 10. So this is the equation for decibels. I explained it before. Okay, if the magnitude of the transfer function is 1, AdB is 0. If it is between 0 and 1, so AdB is negative. But if it is greater than 1, AdB is positive. Sometimes you see minus 3 dB. The people are looking for 3 dB below the gain value or below the maximum value. Why are they interested in 3 dB below the gain or the maximum value? Again, I'll explain it in CDD 2001. Okay. What is the logarithmic of 1 over square root of 2 multiplied by 20? Please calculate it. Do you have calculators?
Negative 3.01.
Negative 3. Negative
0.01.
Okay, dB. dB. Okay, we say negative 3 dB. So if you calculate this one, you will get negative 3 dB. Why do you calculate 1 over square root of 2? The logarithmic of 1 over square root of 2 multiplied by 20. Why? Why 1 over square root of 2, not, for example, 1 over square root of 3?
Because when we calculate H max,
Yes. For the cutoff frequency, when you want to calculate the cutoff frequency, we have 1 over square root of 2 multiplied by H max. So what is H max? The maximum value for the circuit or for our filter, or the gain. When we multiply it by 1 over square root of 2, it means 3 dB below the maximum value will give us the cutoff frequency. So if you have the body plot and you want to look for the cutoff frequency, you just find the maximum value and 3 dB below that and see what the frequency is. So that frequency is the cutoff frequency. That's why we calculate the log of 1 over square root of 2. Okay, let's do an example. Calculate values for C, this is C, R2 and R2 that together with R1 is 1 ohm, produce a low pass filter having a gain of 1 in the pass band. So the gain of the filter is 1 in the pass band and the cutoff frequency is 1 radian over second. Construct the transfer function for this filter and use to sketch a body plot of the filter's frequency response. So we have this circuit. What is the transfer function for this circuit? This is a low pass filter. What is the transfer function? The transfer function is V out over VI. And what kind of filter is it? It's low. What kind of filter? Low pass filter. So because this is a low pass filter at low frequencies, we practically don't have this capacitor over here. So this is what? Sorry, at high frequencies. At high frequencies, V out is 0. So at low frequencies, this is an open circuit. So this is like an inverting op amp. So what is the relation between V out and VI? V out and VI is our transfer function. So find the relation between V out and VI. We just did it. Over here, V out over VI, we have ZF minus ZF over ZI. What is ZF? R2 in parallel with the capacitor. And this is ZI, which is just one resistor. So what is K? R2 over R1, which is the gain. And what is the cutoff frequency for this circuit? We just calculated. So it is 1 over R2C. We don't have the value for R2. We don't have the value for C. But we have the value for the gain. So R2 is K times R1. K is 1. R1 is 1. So R2 will be 1 ohm. So how about the value for C? C is 1 over omega C R2. Omega C is 1 radian over second. And R2 is 1. So C is 1 farad. So this is the final transfer function for this circuit. So it is minus 1 over S plus 1. So how about the body plot for this circuit? The magnitude of the transfer function in dB versus frequency. So what is the maximum value? What is the gain for this circuit? The maximum value for this circuit this must be the gain. What is the gain? R2 over R1. So what is the value for R2 is 1 ohm. What is the value for R1 is 1. So 1 over 1 is 1. So you need to convert it to dB. Why? Because the y-axis is in dB. So what is 1 in dB? 0. Yes. So that's why the maximum value is 0. So if you go down 3 dB, down over here, which is minus 3 dB, you have the cutoff frequency. This one is 1. It is not 0.1. Please correct it in my notes. This is 1. So the cutoff frequency is 1 radian over second.
What do we have to do?
This one is not 0.1, it is 1. Okay, question?
Can you explain how you know that's the cutoff frequency again? Like
Okay. What is the maximum value in dBs? For H max is 0. Yes. So 3 dB below this one will be our cutoff frequency. What is the 3 dB below 0? Is minus 3 dB. So minus 3 dB is here. So from here, it will cut the line. So this point is our cutoff frequency, which is 1. This is not 0.1, this is 1. Okay? You want me to explain one more time? Okay, what kind of filter is it? Is it a low pass filter, high pass, band pass, band reject? Analyze the circuit and find whether this one is a low pass filter or a high pass filter. Any answers? You just analyze it. Justin?
So it would be a high pass because when the frequency is really high, that would just act like a wire and just let the
Which one is the wire?
sorry, the capacitor would act like a wire, just let the current pass through. Whereas when it's really low, that becomes an open circuit and doesn't let anything through.
Okay, you said at high frequencies, the capacitor acts like a wire. So at high frequency,
There's
okay, so what kind of circuit do you have at high frequencies?
just a regular inverting.
Amplifier. How about low frequencies? Why? Because the capacitor. Okay, so when it is open circuit, what will happen to the output voltage? Why? Why 0? Because VP is 0, so it means Vn is 0. So it is like the output is.
There's no current coming in from the source.
Yes, there is no current, so Vn is 0. So it means V out is 0. At low frequencies over here, the capacitor, because the frequency changes, it just affects the capacity, impedance of the capacitor, not these two resistors, just the capacitor. So at low frequencies, capacitor acts like an open circuit, So the output of the op-amp is connected to ground. This is the open circuit. So this is 0. There is no current in this resistor. Because this is 0, this is 0, V out is 0. But at high frequency, the capacitor is a wire, is a short circuit over here. So we have an inverting op-amp. Now, so find the transfer function for this high pass filter. Find the transfer function. What is the transfer function? V out over Vi. So find the relation between the output voltage and the input voltage. Because again, this is now an inverting amplifier, so the output voltage is ZF minus ZF over ZI. So what is ZF? R2, and what is ZI? So from here you can calculate the transfer function. Okay, V out over Vi is the transfer function. What is the relation between V out and over Vi is minus ZF over Zi. So what is ZF over here? R2. So what is Zi?
R1 plus
1 over SC. So what is the transfer function now? R1 plus 1 over SC. If you rearrange the equation, you will get something like this. Is that correct? Okay, this is the transfer function. So R2 over R1, we call it K, which is our gain. What is the cutoff frequency? Is 1 over R1C. So the transfer function is minus K S over S plus omega C, which is 1 over R1C. So why do we call 1 over R1C our cutoff frequency for this circuit? How do you calculate the cutoff frequency? What is the equation to find the cutoff frequency?
Magnitude of hj omega c equals 1 over root 2 times transfer minus transfer minus.
Yes, that's correct. So use this equation and find the cutoff frequency for this circuit. First, we found the transfer function, which is this one. Now we are going to find the cutoff frequency. So to find the cutoff frequency, we always use this equation. So what is H in the frequency domain? Wherever you see S, you just replace it with j omega. So you have H in the frequency domain. What is the maximum value for H? Again, because this is a high pass filter and you have j omega over j omega plus 1 over CR1, because this filter is a high pass filter, so the value for j omega is much greater than this part. So it is like j omega over j omega. So these two guys will cancel out each other, just we have this one. So this is the value for H max. So this is the value for H max multiplied by 1 over square root of 2. But what is the equation for the magnitude of H at cutoff frequency? So the magnitude of this one, this is plus, this is correct in my notes, this is plus R2 over R1. This is the, what is the magnitude of J omega? What is the magnitude of J omega? Is omega. So this is omega because we are at cutoff frequency, that's why we put omega c. And what is the magnitude for this one? Is the square root of the real part square, which is this one, plus the imaginary part square, which is omega c square. Just not j, just the what is multiplied by j, just make that one square. So we'll get this one. Again, this is positive, just correct in my notes. So the omega c is 1 over CR1. Example, we have a body plot of a high pass filter using the active high pass filter shown below. Calculate values of R1, this is R1, R2, this is R2, and use 0.1 microfarad capacitor for this one. And the second part we answer later. So we have this body plot. What is the gain or the maximum value for the transfer function in dB? What is the maximum? From this plot, you have this plot. So what is the maximum value for H in dBs? 20. So 20 is the maximum value. What kind of filter is it? A high pass filter, right? This is a high pass filter. So what is the maximum value for the transfer function in dBs? 20. So 20 minus 3 is 17. At this point, we have the cutoff frequency. This is our cutoff frequency. So we have the gain, which is the maximum value for the transfer function in dBs, is 20. So 20 dB converted to value is 10. The value you see on all the plots for the magnitude of h, j, omega is in dBs. So you need to convert it. So you have 20 dB for k, which is R2 over R1. Now we want to convert it to value. So 20 times log of watt is equal to 20 dB. So k is 10. K is 10. So what is the cutoff frequency? 500 radians over second. So this is the function, the transfer function for this filter. So we have K, we have omega C, R2 over R1 is 10, and 1 over R1C is 500. So we have the value for C, which is 0.1 microfarad. So R1 is 20 kilo ohms, and R2 from this equation is 200 kilo ohms. Is that clear, the procedure, Justin?
Yeah, that makes sense.
So you use the body plot. You found K from the body plot. How? The maximum value you see for this filter, how much is 20 dBs. Again, it is 20 dBs. You have to convert it to a value, which is 10. So R2 over R1 is K. So how about the cutoff frequency, Maxim? How about the cutoff frequency?
Happens at 17 dB.
Yes,
500.
yes. 3 dB below the maximum value, which is 20 over here. So we go down, which is 17. So at 17, what is the frequency? 500 radians over second, which is our cutoff frequency. So we have the value for omega C, which is 500. We found it from the body plot. After that, you can calculate R1 and R2. Questions?
So in this example, C was given.
C was good, yes.
So if we had to do a question like this, say for like a midterm or something, we get like one of the values, the circuit, and the plot.
Yes. I will give you the plot. So from the plot, you have to figure out the values for K and cutoff frequencies. From there, you can calculate R1 and R2. For example, if you were asked to find R1 and R2. Clear? Okay. Practice assessment problems 15.1 and 15.2. How to construct a circuit for a band pass filter using an op-amp or op-amp. So for a band pass filter, we have two cutoff frequencies, omega C1 and omega C2. So for the first step, we need a unity gain low pass filter with the cutoff frequency of omega C2. So we need a omega C2 low pass filter to create the higher cutoff frequency. The second step is a unity gain high pass filter whose cutoff frequency is omega C1. So we need a high pass filter to make the lower cutoff frequency. And after that, we need a circuit to increase the gain. So that is the circuit, we call it gain cascade bandpass. So we need 3 circuits. One, to create the low pass filter. Second, to create the high pass filter. And the third acts as a gain. So the cascade of these 3 circuits will give us a band pass filter. So this is a circuit for a low pass filter, and this is the circuit for the high pass filter, and this is an inverting amplifier. Why do we use an inverting amplifier over here? Because of the gain. You want to, because these are for unity gain, these 2 filters. So if you want to increase the gain, you put it from, for example, from 0 for this body plot to 20. So you need a circuit, a gain circuit. So that's why we have this circuit over here. So what is the transfer function for this circuit? V out over VR. How do you calculate that?
You'd have to find the first like output of the low pass filter and then use as the input as the high pass and calculate the output for the high pass filter and then use as the input for the converting.
Yeah, if you do that, what will be your final answer? Okay, so how do you calculate maximum is right? Well, how do you calculate the transfer function for this circuit? What is the transfer function for this circuit? Output voltage over the input voltage. V out over Vi, the output over the response. So what is the output at this node? Low pass filter. You have the transfer function. Check in your notes. R2 minus R2 over R1, because both of them are equal, RL over RL, we just have minus. And omega C2 over S plus omega C2. Why omega C2? Because we want this low pass filter gives us the higher cutoff frequency. And what is the higher cutoff frequency? Omega C2. So this is for this output. So because this is now the input for this high pass filter, so the relation between this one and this one is R minus RH over RH, which is minus 1, S over S plus omega C1. Why omega C1? Because we want this high pass filter to create a lower cutoff frequency up to here. And what is the relation between V out and this? Is R minus RF over RI. So we'll get this one. The relation between V out and Vi, which is our transfer function. Is that clear? Just rearrange the circuit, the equation. This is the transfer function. Because we are using a broadband filters, it means omega C2 is much, much greater than omega C1. So for this one, we can say omega C1 plus omega C2 is about equal to omega C2. That's why over here we have just omega C2. And this will be the transfer function for the mentioned band pass filter. So what is omega C2? 1 over RLCl. And what is omega C1? 1 over RHCH. Any questions? Questions?
Did you calculate the cutoff frequency for each of them like individually by using the transfer functions of the low pass
Yes.
and the high pass?
Because we have individual circuits and we want the low pass filter to create our higher cutoff frequency, so then we use the cutoff frequency of the low pass filter for omega C2. And what is the center frequency? Center frequency for band pass filter or for band reject filter. I explain. The center frequency for a broadband filter from the name is the midpoint between two frequencies. But you remember in ECED 2001, if you find the midpoint of two numbers, you say, for example, between 2 and 12, you say 2 plus 12 divided by 2. But over here, I said, no, you cannot. You find the midpoint like this for the filter. You need to get the square root of the higher frequency multiplied by the lower frequency. Remember? Why? The center frequency, if we had a narrow band filter, you could find the midpoint like the higher plus the lower cutoff frequency divided by 2. That would be your midpoint. But when you have a broad band filter, the center point is the square root of the higher frequency multiplied by the lower frequency. And we call this point geometric midpoint. Why do we do that? Because we want to get the same area between the lower cutoff frequency at the midpoint and the area from the midpoint to the higher frequency. That's why for a broadband filter, the midpoint is the square root of higher frequency multiplied by lower frequency. And the magnitude of the transfer function at the center frequency, if you calculate from here, will be K. What is K? RF over RR. It means at the center frequency, you will get the maximum value for the transfer function. So at the center frequency, you will get the maximum value for the transfer function. And this is the proof. Why omega C1 multiplied by omega C2 minus omega naught square, which is the center frequency square, is 0? Because omega C1 multiplied by omega C2 is omega naught square. Or the center frequency is the square root of omega C1 multiplied by omega C2. Is that clear? Yes? Practice example 15.5. Any questions? Okay, Have a great weekend. Enjoy your time. Be happy.